Hi everyone, my name's Claire and I'm an astrophysicist currently working at the University of Melbourne. Your teachers have asked me to put together a little presentation for you today. Science Week's coming up soon, and also I believe you have a unit on the Earth, the Sun and the Moon. I also want to tell you a little bit about what it means to be an astrophysicist, the sort of perks of my job and what I do day to day in my studies and also in my work. So if that interests you, come along and I'll show you what I get up to.
Hello, I'm Stella, a plain-speaking alien. I like to explain words in easy-to-understand language. You don't have to know these words to enjoy the talk, but if you do want to know, look for me and I'll tell you what they mean.
One of the questions that we ask ourselves from a very early age is, who am I? And I'm going to try and answer that question for you. But I think first, the question I might answer is, what am I? I call myself an astrophysicist. What's that? Well, astrophysicist is made of two basic words, astro and physicist. So the word astro is star or space in ancient Greek. Bonus points if you can identify the ancient Greek landmark there. Physicist has an interesting root word. It can come from the Greek physika, or knowledge of nature, or from physic, physica, physique, in Latin or Old French. But this root of the word physique means physical or medicine. And again, bonus points if you can identify these two landmarks. So put it together, an astrophysicist means knowledge of nature in terms of stars and space. So basically, I find out stuff about space. I want to know what's in it. For example, that planet in the middle, which you probably have recognized as Saturn, and also on the left there. Now that's an image from a satellite called the Hubble Space Telescope, and that's looking deep, deep into the sky at galaxies a long, long, long way away. Everything you can see there is a galaxy, except for the thing that looks like a star, which is a star. I want to know, how does the stuff that's in space behave? Does it move or change? Does it orbit stuff? Does it explode? For example, at the top there, you're looking at the Crab Nebula. This is called a supernova remnant, and it's in the constellation of Taurus. It has a pulsar right in the center of it. It didn't always look like this. This is what's left over after an explosive supernova. At the bottom there, you can see our sun. Our sun can be quiet, it can be boisterous. We're talking sunspots, flares, prominences. The sun sends material out in all directions, streaming past Earth and out into the outer solar system. Not just light. It's orbited by a bunch of planets. We can work out its mass as well. I want to know, has it always been like that? Do the individual things in space change? Does the universe change? At the top there, you can see an image describing the life cycle of stars from birth to death, ending their lives as white dwarfs, black holes, pulsars, and also explosions leaving nothing. On the right-hand side, you can see the evolution of the universe. When you look out into the sky, this is not how it's always looked. There's a lot of evidence that suggests the universe has changed over time. Wow, that's a lot! And it's way too much for one person to properly study. So us scientists usually focus in on one tiny little area. I specialize in a special type of galaxy called a quasar. What? Quasar. Now the word quasar is a contraction or a smushing together of the words quasi which means to look like, and stellar, or star. And this is because when they were first discovered in the 1950s, they looked just like stars. But when they were investigated a little bit further, it was clear that they couldn't be stars. They behaved very weirdly. So they were called quasars from the 1960s. This is an imagination drawn by an artist of a quasar called ULAS J1120 plus 0641. Those numbers at the end of the name actually designate whereabouts on the sky it is. We can't ever show you a real picture of the center of a quasar because it's so small on the sky. We will never have a telescope big enough that can zoom right into the center. What's a quasar though? Well, they're basically really big galaxies, so groups of stars. You might remember that the Milky Way is the galaxy that our solar system is in. And these big galaxies called quasars are special because right in the center, they have a huge, hungry, supermassive black hole. How big is supermassive? Well, we don't even talk about black holes in terms of size like you might be used to. The sun is ginormous, right? So imagine 10 of those. Wait, no, 100. Actually, it's between 1,000,000 and 100 times 1,000,000 masses of our sun. And it sits right in the center of the galaxy in this little area we call the active galactic nucleus, or AGN. Surrounding the supermassive black hole, there's a disk of material, dust, gas, and sometimes bigger chunks like stars, which goes around this huge supermassive black hole, spiraling around and eventually falling in bit by bit. We call this the accretion disk. The environment here is super intense, and there's a lot of friction as bits of stuff move past and hit and rub against other bits of stuff. So lots of different types of light energy is produced, like X-rays, just like you might get if you break a bone. Ultraviolet, like what burns your skin if you're out in the sunlight. Visible light, of course what you can see. Infrared, like what a heater or a stove gives off. And many other types of light that we collectively call radiation. Now, before the light from the accretion disk even makes it out into the galaxy, it hits a bunch of gas hanging around outside, and it lights it up. Kind of like if you're driving in fog on a dark night, and your car's lights can't really get through the fog. These gases then make their own light, depending on how thick or dense they are, and also what they're made of, as well as how much energy from the accretion disk light they are receiving. We then see this light on Earth, and my job is to compare the signals from these gases with computer simulations to try to work out what's going on in there. We still really don't know. How on earth did I get to be doing this? At school, I always loved science, from space to dinosaurs, but I also love music, sport, art, languages, writing, and, well, everything. I've always been a bit of a curious George about everything. But I ended up finishing my high school with a few sciences, languages, maths, and writing subjects under my belt. And importantly, I also discovered double bass halfway through year 11. So for some reason, I decided to start my university career in a music degree at the University of Melbourne. I also studied a bit of German. A couple of years into my degree, I sort of realised that even though I loved music, I didn't really want to do it for a job. So I had a look around and I changed to a science degree. In my science degree, I studied geology, or rocks in the earth, and also a type of science called mathematical physics, which is basically the maths we use to describe our natural world. I didn't waste my music though. I turned it into a diploma, which is like a little degree, along with another little degree or diploma in criminology. I told you I was interested in everything. After I finished my degree, I worked in a gold mine for a little while, and then I moved to Abu Dhabi for a year for work. And after that, I moved to England. I decided to study and work as a teacher at the University of Nottingham, and then I also did some studies in astronomy by distance, so online, with Swinburne University. When I came back to Australia, I originally was a science, physics and maths teacher at a high school. But then I decided to come back to the University of Melbourne to study more space, to study astrophysics. What does life even look like for an astrophysicist? First of all, it's not all serious. And plus, I do like a good orange. As a student, and for my job, I have been incredibly lucky with all of my experiences. I've travelled extensively. I went to Sydney for a workshop and visited the Sydney Observatory. I learnt that there are some things that you shouldn't touch unless you want to get grease all over yourself. I've also been to New South Wales many times, Western Australia, South Australia and Canberra for my studies and my job. I was lucky enough as a student to be selected for a flyover trip to Antarctica, so I caught a Qantas flight from Melbourne, flew all the way down and along the coast. I took some measurements of the Earth's magnetic field as we flew over the Earth's magnetic pole, and I spoke to a lot of interested students. As part of my studies, I also got sent to Hawaii twice, once in 2014 and once in 2016, to visit people there who helped me with my research. I also took a bit of time off and did a little bit of tourist holidaying. I went to Munich in Germany last year for work, and I attended a conference. This is a group of all the Australians that attended the conference. As a student, I also went to Belfast in the UK in 2015, and also in 2015, I went to Penn State University in the USA. 2015 was a crazy year of travel for me as a student. Something I have been really lucky to be involved in as part of my job is called the Kathmandu Astrophysics School. So far, we've run 2 of these, one in 2016 and one in 2018, and we've just received a grant from the International Astronomical Union to run CAS 2020 or possibly 2021, depending on coronavirus restrictions. Kathmandu Astrophysics School is really cool. I go to Nepal with a bunch of other international lecturers, and we run a residential school for graduate students. We teach them lots of skills, including presentation and teaching skills, along with astrophysical and computational skills. It's lots of fun, and it's great to be doing work that puts back into the community. So I've also written some stuff, and I was lucky enough to have this published online on phys.org and also in the University of Melbourne's online magazine called Pursuit. You can actually still find my article called Putting the Universe Under the Telescope online. Some of my astrophysical research has also been published in the Astronomical Journal. And I've also been part of a paper that got published that was about my work with telescopes in schools. So in my job, I use a whole lot of skills I've picked up in my different studies and travels. I run a program that I just mentioned called Telescopes in Schools, or TIS, where the TIS program lends a telescope to a school for a few years, and I teach the teachers to use the telescope, and we run observation nights. My job involves running development for teachers, working with students and the general public in workshops, lectures, talks, and telescope observation nights. I run the School of Physics Work Experience program, which now sees more than 80 students come through doing astrophysics, particle physics, and nanoscale imaging for a whole week in a top quality program, gaining valuable experience into what it's like to be a student and researcher in these fields. Maybe one day I might see you. One of the things I absolutely love doing in my job is media. I've probably been on the radio maybe about 10 times. Very lucky, get to talk to ABC's Miff Warhurst and now Jacinta Parsons about all sorts of science things. Last year, I did a public lecture with my friend, Professor Kenny McAlpine. It was called The Sounds of Space, and it was about how physics and science can be reflected in sounds. It was really cool, and it got made into a podcast, which you can still listen to. Every so often I get contacted to do voiceovers for documentaries and also advertisements, which you can find on YouTube. One of my favourite things to do is TV, and I've been super lucky quite a few times to be contacted by ABC News to give interviews on recent science developments, such as the first female spacewalk, getting rid of IPK, the reference kilogram, and many other things. I've started to branch out into my own YouTube channel, and of course I have some socials. You can find me all over as RedLippedAstro. So onwards, you want to hear some science, right? Hopefully you are quite familiar with these two things. Of course, here we have the Earth and the Sun. You probably know that the Earth is called a planet and the Sun is called a star. But do you know the difference? Planets do not produce their own energy or light. Stars produce their own energy deep inside their cores, where atoms are forced together, and they radiate and shine light out from their surfaces, which then hits planets and reflects or is absorbed by them. Planets orbit stars. For example, the planets in our solar system go round the star, the Sun, and stars are orbited by planets. Some stars are actually in orbit with other stars called binaries or multi-star systems. Planets can be really different from each other, and in some ways, every planet might be considered unique. Stars come in many different types, sizes, temperatures, brightness, but we are able to link them together and categorize them into their own stellar types. Planets are made up of a lot less material than stars, so they have less mass. And stars, of course, are made up of a lot more material than planets. And this is the reason that stars are actually able to produce energy, because all of that mass produces enough gravity to force those atoms together in the middle. Planets just don't have enough material to do this. Right, on to some facts, hey? We just mentioned mass. Let's talk about it for a minute. When we say that the Sun is really big, or the Earth is really big or massive, do you have any idea what that actually really means? Do you have any feel for what those big numbers are? Well, it's actually quite difficult. So if you went down to the supermarket and you picked up a fairly average sized pumpkin, that pumpkin, let's say it weighs around 6 kilo. If you wanted to make an Earth out of pumpkins, you would need to take 1 million of those pumpkins and squish them together. Then do that 1 billion times, squish it together. Then do it again 1 billion times. And then the amount of pumpkin mass that you've got is the same as the mass of the Earth. That sounds pretty big. But if you want to make a sun out of your pumpkins, you need to take 1 million of those pumpkin Earths and squish it all together. So we're talking really, really big. But guess what? The Sun isn't even a particularly massive star. How about distance? When we say the Sun is quite a long way away from Earth, do you have any real feel for that? Well, it's actually really hard to imagine, but I'm guessing you've probably run cross-country races before. So, you know when you run a kilometre? Well, if you wanted to get from the middle of the Earth to the middle of the Sun, you would need to run that kilometre 151 million times. That's a long way away. And you'd probably be pretty tired. The large-scale phenomena that we see and experience on Earth is due to our planet's position in space. One of these phenomena you would know is day and night. So the reason that we experience a daytime on Earth is because we happen to be facing the sun at the time. And the Earth rotates around its axis. You can see that axis there marked on the diagram with a white dotted line. And the Earth revolves around this, a bit like if you have a lollipop and you twist the stick. Countries that are in the shadow of the sun experience night. So as the Earth turns around, opposite one side is the day and the other side is experiencing night. You probably know that the length of a day is about 24 hours. What this means is that it takes 24 hours for the spot you're standing on to go from where it is all around the axis and back to where it is. This is actually not the same for all planets everywhere. For example, Venus, when it rotates on its axis, is super slow. It takes 116 Earth days plus 18 Earth hours to spin once on its axis. So while we're on Earth and the sun, I have to admit, I just lied to you. I showed you a diagram, just for ease of explanation, that showed the axis upright. This is actually not quite what happens. It turns out that the axis, or the lollipop stick, is actually tilted from up and down by about 23.5 degrees. That doesn't sound like a lot, and it doesn't sound like it would do very much, but actually this is the reason that we have seasons. So, of course, when I'm talking about seasons, I'm not talking about salt and pepper. I'm talking about winter, autumn, spring and summer. If you have a look at this diagram, you can see the tilt always stays the same direction as the Earth goes around the sun. When the Earth is the first position on the diagram, the northern hemisphere, the top half of the globe, is tilted away. It is experiencing winter because it gets less light overall on its surface. You will probably notice that the North Pole, where the axis comes out the top there, doesn't actually get any light at all during the day or night at this time of the year. Looking at the southern hemisphere, it's tilted towards the sun, meaning that it receives more light overall on the surface down here at this time in the year, and the southern hemisphere, including Australia, experiences summer. Looking at the South Pole, you can see that as the Earth rotates, giving day and night, the South Pole always gets light, giving the South Pole and Antarctica 24 hours of daylight. When the Earth is on the opposite side of the Sun, the third position on the diagram, the northern hemisphere is tilted towards the Sun, meaning more light hits the surface, giving summer, whilst the southern hemisphere has winter. At positions 2 and 4 of the diagram, neither the northern nor southern hemisphere are pointed towards the sun, meaning that both hemispheres receive about the same amount of light on their surfaces. Right in the middle of this period, day and night are the same length, and we call this the equinox, which is Latin for equal night. These two times in Earth's orbit are our spring and autumn seasons. Look at these awesome images of the Earth from EUMETSAT's Meteosat 9 satellite made into a video. You can easily see how the southern hemisphere receives more light, experiencing summer, at the same time as the northern hemisphere receiving less light and experiencing winter. When the shadow line is exactly down the middle of the Earth, neither hemisphere receives more light than the other, and we call this the equinox. Not all planets experience night and day and seasons the same way that Earth does. We saw that Venus has a different length of day, but for some planets, the same side of the planet faces the star all the time. So what that means is that for every orbit around the star, the rotation on the axis takes exactly the same amount of time. For these planets, the side permanently facing the star always has light on it and so is always warmer. And the other side, the dark side, the faraway side, is cold. We call this phenomenon tidal locking, and we're going to talk about that in upcoming slides. Hey, recognize this? This is a satellite, which is a word we use to describe anything going around the Earth, or even around the Moon or another planet. We also call it the Moon, of course. But moon is a word we use to describe many different bodies in the sky. You probably know of many others, and there are definitely many more that neither you nor I or anyone has ever known about. How well do you know your moons? One of these is called Io, one is called Iapetus, and the other is called Europa. Do you know which is which? Io is a moon of Jupiter, and it's coloured yellow by its surface coating of sulfur and sulfur dioxide frost. The blue one is called Europa, and it's another moon of Jupiter. It's thought to have a water ice surface with salty water in oceans underneath. The last one, the one that looks like it has been splashed with mud, is called Iapetus, and is a moon of Saturn that is tidally locked. Remember we mentioned that before? So the bright face always faces Saturn, and the dark, dirty side, which is probably due to dirt being carried there when ice on the sunny side melts and refreezes over on the dark side, that always faces away. We have one moon. Mercury and Venus have none, but every other planet in our solar system has more than one. Mars has 2, and Jupiter has 79. As the moon goes around the Earth, the force of gravity, much like what keeps your feet on the ground and what makes your pen fall when you drop it, between the moon and the Earth is trying to pull them closer together. Because the moon is moving around fast enough, it's able to keep going. It's a bit like if you tie a ball on a string and circle it fast enough around your head. You feel the tug on the string, but the ball keeps travelling around. Now, the hard rock on Earth doesn't really move with the pulling, although the pulling does affect the water in the oceans on Earth, and it squashes the Earth into a bit of a funny flattened sphere. We call this shape oblate. Where the Earth is fatter, that is where the moon is directly near and also directly on the opposite side from the moon, there's a high tide. As the moon moves around the Earth, the high tide follows. This is where we get our tides. The moon always shows the same face to the Earth because its rotation on its axis is the same as the time it takes to go around the Earth. We've already mentioned this. It's called tidal locking. And this is why we never see the other side or the far side of the moon. So let's put the Earth, the moon, and the sun together. Remember that the Earth orbits the sun, while the moon orbits the Earth. We need to understand the Earth, moon, and sun system in order to explain the phases of the moon. So if this is a bird's eye view, with the Earth going around the sun and the moon going around the Earth, if you look at the Earth, you can see that half of it is in shadow. This area is the nighttime. Just like the Earth, the moon also always has half of it in shadow. And it depends where the moon is around the Earth as to which phase of the moon you see. That is, how much of the half face of the moon that you see. When the moon is lined up with the Earth and the sun, if it is on the other side of the Earth, you see a full moon. If it is between the Earth and the sun, you don't see it at all. It's completely in shadow. This is called the new moon. Looking at this diagram, we also see quarter moons and gibbous and crescent moons. In this case, waxing means that it's heading towards more light that you can see. So it goes from waxing crescent to first quarter to waxing gibbous, and waxing gibbous to full moon. And waning means that it's getting less. So it goes from full moon to waning gibbous to third quarter third quarter to waning crescent, and then on to the new moon. I want to remind everybody at this point that none of the diagrams in this talk are to scale, which means how you see it on the screen isn't really a reflection of their true sizes next to each other. If something's not to scale, it also means that you might have, say, an ant drawn as big as a human. Usually we just do that to explain something. If all of the diagrams were to scale, you probably wouldn't be able to see anything very well. The Sun is almost 400 times as far away from the Earth as the Moon is. The Sun is huge too, and the Moon is relatively little. Due to the Sun's distance, which is very large, it takes up about half a degree on the sky, so about a thumb. So if you turn 360 degrees, you are turning a full circle. 1 degree is going around only a little bit. The amount is if the circle was chopped up into 360 pieces. Half a degree is half of that little bit. The Moon is much closer, but also much smaller. The amazing coincidence is that because of its exact size and distance, the Moon also looks like it takes up about half a degree on the sky. So if it happens that the Moon is orbiting Earth and gets between the Sun's light on the Earth during the day, we get a solar eclipse. What you can see here is that the Moon is lined up directly with the Sun and the Earth. Umbra is Latin for shadow, and that tiny little point on Earth is where people will experience a total eclipse. Penumbra is Latin for almost or nearly the shadow. And in these areas, people on Earth will see a dimming of the Sun, but not a full eclipse, which means it won't look like the Moon completely covers the Sun. Here's a bunch of photos taken with a filter of the Moon as it approaches. It gets in between the Sun and the Earth, and then covers the Sun fully like a disk. That bright spark in the middle is called the ring of fire. And then you can see the Moon slowly moving on and no longer blocking the Sun. Solar eclipses have an impact on the natural world. A lot of animals get confused or go to bed. And throughout human history, people have often been really scared of this phenomenon, mostly because they didn't understand it. A lunar eclipse occurs when the Moon is on the other side of the Earth. So the Earth is between the Moon and the Sun, and the Moon is in the Earth's shadow. These are really pretty and often called blood moons because they look so red. Things around us are constantly changing. Caterpillars become butterflies, night becomes day, winter becomes spring, and we all grow older. Some of the things that change happen in cycles. Some change permanently over time. However, when we look closely at these things, we can start to find patterns. This is what science is all about. Taking measurements, looking for patterns, having a think, and then testing what you think. One of the best ways to test is to make a prediction and see if it comes true every single time, not just a couple of tests. For example, if you follow this chart, you make a prediction and a test. If you're wrong, you need to start again. Find a new idea and test that. If you're correct, guess what? You need to test more times. Keep testing and testing and testing. And all you can ever say is that you're correct so far. The minute your test fails and it shows that you're wrong, you need to go back to the start, have a think about your model or your idea, and change it, and then begin the cycle again. Even this process has changed over time, from the ancient natural philosophers to now, making this process better and our knowledge of the world deeper. Stuff changes for us all the time, and it has been so important in some ways. For example, Earth didn't always look like this. A long time ago, Earth was formed by the coming together of lots of bits and pieces of material that we're in a disk around our newly formed sun. Earth has experienced a very large number of natural events, from glaciations, volcanoes, asteroids, and all this sort of thing has forced life to evolve and adapt, ultimately giving us strength and more variety. Importantly, though, these things have not happened so much that everything was wiped out. We talked about the moon. It's getting further and further away every year by about 3.8 centimetres, and eventually it'll settle into a position where it goes around the Earth once every 47 days. That's pretty much twice as long as it takes to go around now. Eventually the sun is going to run out of hydrogen fuel and engulf the Earth. It will become more than 2,700 times brighter and will expand maybe even out to beyond Earth's orbit, swallowing Earth and the moon, and of course Mercury and Venus up in the process. So just because things look like they're staying the same doesn't mean they actually are, or they always have, or always will. But don't worry about the sun. That's not for another 5 billion years. If you work out how to live that long, you make sure you tell me. Earth is unique. We need to take care of the Earth. It supports us. It's the only place we know to have life, and so far the only one proven to sustain life, our life. It supports us with air, light, food, and warmth. As of July 23rd, there are 4,197 confirmed exoplanets. That's planets orbiting other stars, not our sun. And there are many, many more good candidates that we know about. We haven't found anywhere in our own solar system, or even other systems, other exoplanets, that is the same and could support us as easily as the Earth does. Even if we did, we don't really have the technology yet to move there. Some food for thought for you to take away is, if we've already wrecked our own planet, which gives us air, light, food and warmth, and we have to leave, would it be the right thing to do anyway? So that's it. We've talked a bit about what astrophysics is and what an astrophysicist does. I've told you a bit about the perks of my job and what I get up to and what I study. I hope that's motivated you maybe to think about doing science, or at least to enjoy it, and also just question the world around you. I talked to you a little bit about how I got to where I am, and hopefully you understand that life doesn't proceed in a straight line, and sometimes we change our minds about what we want to do, and that's perfectly okay. The most important thing is that you keep asking questions and you keep staying interested. I hope I've helped you understand a little bit more about night and day, seasons, eclipses, and how the Earth and the Moon and the Sun system brings about a lot of what we see around us. The Earth is truly unique. It's the only planet that we can survive on that we know of. So we need to take care of it. And what better way to take care of something than actually understanding how it all works? Thanks for coming along with me, and I hope to see you around.